and welcome to a presentation for Cambridge University Press on vectors. We're going to look at the three different chapters in the Extension 1 and Extension 2 textbooks that relate to this topic. Hello and welcome to the third of three videos that goes through the vectors content of the Cambridge University Press textbooks. This particular video is looking at Extension 2, so the Extension 2 chapter, and the chapter that we're looking at there is Chapter 5. Here's the breakdown of that chapter with the syllabus references there. So first of all, just a quick making sure that we understand what we mean by coordinates in 3 dimensions, then introducing the idea of vectors in 3 dimensions, bringing the dot product across from 2 dimensions to 3 dimensions, and the same with vector proofs, and then finally an extra bit where we have a vector equation of a line in both 2 and 3 dimensions, and also looking at vector equations of circles, spheres and planes. So looking at coordinates in 3 dimensions then, we need to be able to write coordinates of a point, draw some axes. There are various conventions around this. Look at Pythagoras' theorem to get the distance between 2 points, and the midpoint formula, distance between 2 points. And also just consider for a minute the equation of a plane, as it makes life a lot easier if we can refer to planes when we're talking in 3 dimensions. So transition from 2 dimensions to 3 is really quite straightforward if we've just got Cartesian coordinates in 3 dimensions. So we've got the 3 axes, the x-axis, the y-axis and the z-axis. They are all mutually perpendicular to each other. And one of the things to practice here is a bird's eye view, so looking at things from the side, from the top. What does that look like? What shadows will things cast and so on. GeoGebra, which is a free online program, has an excellent 3-dimensional program for drawing, which I've used throughout this PowerPoint in places. And I'd certainly recommend you either using it yourself or even getting your students to have a play around with it. Even just something as simple as plotting a point and then spinning that around can be quite effective. So looking at how we draw our axes, the 3 axes need to form a right-handed set. Now what we mean by that is if you're to hold up your right hand, you might want to try doing this while you're watching this, in the way that this diagram shows, a sort of Spider-Man firing a web type idea. You've got the thumb is the x-axis, the first finger is the y-axis, and the second finger is the z-axis. That means we can actually put it in different ways. So all of these, you might want to pause the video and try. If you've got your right hand set out that way, you can fit your right hand against all of these different ways of doing it. So any of them would be completely acceptable because they're all a right-handed set. One of the reasons for having vectors in 3 dimensions, in fact one of the reasons for having vectors at all, is because it's very difficult to define gradient or slope in 3 dimensions unless we've got some sort of vector notation way of describing that. So the distance and midpoint formulae are there in the textbook. It's just a quick extension of Pythagoras' theorem, and there is a proof there in the textbook for you to go through as well. The other thing that I'd like to point out from this part of the chapter is just to think for a minute about planes parallel with the coordinate axis, which is just an extension of vertical and horizontal lines in 2 dimensions. So just getting used to talking about those. From there then you can go straight into just practicing a few quick questions. And I wouldn't spend too long on this exercise unless you've got a very weak class, just to make sure that they're okay with coordinates in 3 dimensions. And finding a couple of things, distance between points, to perhaps to do something like we're doing in question 12 here to show that a triangle's isosceles, for instance. So then we head straight on into 5b, which is where the real stuff starts. So vectors in 3 dimensions, we need to look at the different types of notation, some angles between the vector itself and the axes, the magnitude, and perhaps dividing a line in ratio. So first of all, here's my right-handed axis. We've got a vector, and we can express that vector in terms of I and j as previously, which is my x and y, so I'm going to add a k to that. So notice that all my column vectors have now got this extra line on the bottom because I'm now expressing it like 3-dimensional coordinates in x, y and z. And so I've got I, j and k when I'm writing it in component form. As we have a quick look at an example such as this, we've got a cuboid and we're told that OA is 3J, OC is K and OD is I, and I might just write those on there like that. So if we're trying to express some of these other vectors in terms of I, J and K, we can just use it in the same way as we did in 2 dimensions by going along paths that we know, except that now that those paths that we know might be in 3 dimensions instead. So to get from O to E, I'd have to come along OD, and then I'd come along DE, which is the same as OA. So here's the path I'd travel, and that gives me that OE is I plus 3J. If I was doing OF, I could also do OE that way as well. Same thing. It's normal convention to write the I, J and K in alphabetical order. OF, I would get from O to F, for example, this way. There are other ways, but this is a way of getting there. So I've got an I, I've got a K, and I've got a 3J. And I'd write those like that, or better, in alphabetical order. To get from G to F, I might notice that that's just 3J. And from G to B, I've got to go along the 3J, and then I've got to go in the negative I direction. So then M and N are midpoints of OD and GF respectively. So to find MN, I need to go half the distance along OD up to G, and then half the distance along from G to F. And you can put it together like this. So it's exactly the same as in 2 dimensions, except that it's now in 3 dimensions. Addition, subtraction, multiplication by a scalar all work the same way. And let's look at an example. So suppose I've got an example like this one. A is 111, B is 1345, and I'm going to find a point P such that it's in a certain ratio. Here's a picture I've drawn of it. I've done that in GeoGebra 3D. As I say, do try using that. It's a great tool. And it helps me see that I want to put P there such that it's in a particular ratio. In other words, I want AP to be a quarter of AB. And I can write AB and AP like this. I know that already from what I know about vectors. And that means that basically I want this to be true. That means I could rearrange it so that I could write for P, P being the position vector of P, which is what I'm trying to find, as being B plus 3A. And I've got both those things, so now it's just a bit of algebra. And we're there. Magnitude. Let's talk about magnitude for a minute. So magnitude is going to be an extension of Pythagoras' theorem into 3 dimensions. So here's OA, and I'm going to use Pythagoras' theorem twice. And of course what helps here is if students had a good familiarity when you're doing 3-dimensional Pythagoras or trigonometry earlier on. And just making sure that they understand what's going on there. But basically we can show fairly straightforwardly that the magnitude of a vector OA, where OA is xi plus yj plus zk, is just x squared plus y squared plus z squared, and then squaring rooting that to get the actual magnitude. In the reference sheet for NESA, they only give it in 2 dimensions, so we need to make sure that students are aware that that can be extended into 3 dimensions. We can also talk about direction in 3 dimensions. Remember, in 2 dimensions we talked about a vector having length magnitude, but also having that angle direction. Now, of course, we're in extension 2, so we could now talk about that as the argument if we want to start making references to complex numbers, being very careful, of course, not to get our eyes confused. But we need to talk about direction in 3 dimensions, and to do that we need to talk about something called the direction ratios. Now, it doesn't say direction ratios in the syllabus, but then they've got a question in their sample exams that basically uses these direction ratios. So whilst it doesn't say specifically to do them, I think it's very important that we do, because they utilize them in one of their questions. So it's one of these things that's sort of innate when we're talking about direction in 3 dimensions, so important that we cover it, I think. So if we look here at a vector OP, where P has these particular coordinates, What we need to try and visualize, and this is where GeoGebra would help you, is that OCP is going to be a right angled triangle with the right angle here. OCP is the right angle. OAP is also a right angled triangle where OAP is the right angle, and OBP is a right angled triangle where OBP is the right angle. And so in using that, we can use some three-dimensional trigonometry here, because I'm going to say that the angle from the y-axis to OP is beta, from the x-axis to OP is alpha, and from the z-axis to OP is gamma. Tricky to draw these in 2 dimensions, so that's where GeoGebra helps us. You can spin it around and have a look at it. But that means that we've got these particular angles, and using some trigonometry we can write down that we've got these cosines, and what we call them is direction cosines. So cos of alpha is A, which is the x coordinate of P, over the magnitude of OP, and so on. Remembering that we've called OP R, that means we've actually got direction cosines of R as below. And that we can also write the magnitude of OP. We've already established that that's a squared plus b squared plus c squared all square rooted. So we've actually got that cos squared alpha plus cos squared beta plus cos squared gamma works out to be 1, which has got to be useful at some point, isn't it? Now actually what Ness's sample question does is goes through that and proves that in a sense, but it uses the dot product. So I will cover that particular example question because it's quite interesting, but just a little bit later. So we've got a displacement vector then, v. It's got the same direction as the position vector. So if it's not coming out of the origin, it's just somewhere else, then that would work the same way. The direction cosines would all be the same, and that would just sit somewhere else on the whole plane. So here's an example. Suppose I've got a vector v is inclined to the x-axis at 45 degrees and the y-axis at 60 degrees. Find its inclination to the z-axis. So we've got a magnitude and we're asked to express v in a particular form. So we can write down the direction cosines. We know 2 of them, we just don't know the other one. And we also know that the 3 things add up to 1. So I could then find that cos of gamma, where gamma is the angle between the vector and the z-axis, could be written as plus or minus a half. So either 60 degrees or 120 degrees. Now that means that we could write down, if we look, that we now replace that with the plus or minus half that we know, that means I could write down v, the vector v, the unit vector v, using these particular cosines, the direction cosines. And if I know the magnitude is 12, I've just got to multiply that unit vector by 12 to get the magnitude, to get the vector v that has length 12 units. And I can multiply that out like that. Notice I still have the plus or minus there. So at this point we could do some questions from 5b. We do that. I've picked out these particular ones as just giving a nice overview. Covers in a few things that would be useful. And then we go on to 5c. So we're looking at the dot product. First thing to establish there is what are we actually going to mean by the angle between things in 3 dimensions. It looks a little bit at the triangle inequality, which we've covered a couple of times up to this point if you're working through the book in turn, both in chapter 2, but also briefly in chapter 3 on complex numbers as well. And it also talks about the orthonormal. So visualizing the angle between 2 lines in 3 dimensions, here's my 2 vectors, or lines. And using the dot product, which we're bringing across from the 2-dimensional work that we've done, we have this formula. And if cos theta is 0, then that implies that b1 and b2 are perpendicular to each other. So what does it mean for 2 vectors to be perpendicular to each other? Well, we need to be just a little bit careful here, don't we? Because in 2 dimensions, when 2 vectors are perpendicular, that means that they will touch. But in 3 dimensions, you could have 2 vectors that are perpendicular that don't touch. So here again, 3-dimensional GeoGebra would be a good thing to show that. I think it's worth going through this particular example in the book, worked example 10, that goes through using the triangle inequality. And I think this example 12 that discusses the idea of vectors being orthonormal, i.e. they are all mutually perpendicular to each other. So take any two of them, they'll be perpendicular to each other, like the x, y and z axis. And also that each is a unit vector. So that example goes through that and it introduces this idea of vectors being orthonormal. And then we can do some questions from 5C, practicing finding the dot product, but also having this idea of putting in some sort of variable and using the information such as them being perpendicular to find that missing variable. And some slightly trickier ones where we've got this idea that we've met before of sort of multiplying out brackets with the dot product, so this left hand side here becoming a dot b plus a dot c, for example. And then we want to look at some applications for the dot product, and this is where we bring in this idea of direction cosines again that we just met back in 5B. And this Nessa example is a good one to look at here. So let's have a look at this. This is the sample that I'm talking about from the Extension 2 sample exam. We've got a particular point with a particular position vector, and we're told the vector OA makes these angles with these axes. And we're asked to take a dot product with the three unit vectors and to prove that therefore the result that we had before is true. So let's take this point x, a vector x, ABC, which is the position vector of A. We can work out the modulus of that, and we know that alpha is the angle between OA, which we're now calling x, and the I direction. So x dot I would be the modulus of x times the modulus of I being just 1, of course, times cos of alpha. Now we can work out x dot I by doing that, and we just get that that's just A. So we've therefore got that A is the modulus of x, which I'm now expressing as the square root of a squared plus b squared plus c squared times cos of alpha. In other words, I can write cos of alpha is A all over square root of a squared plus b squared plus c squared. Now, without spending the time doing it, we could do the same thing, of course, for beta and gamma. Exactly the same process. And once I've got that, then I can simply write that cos squared alpha plus cos squared beta plus cos squared gamma can be written using these formulae I've just worked out, and then it's a fairly straightforward step to show that that is therefore 1. But in order to do all of that, we need to understand what the direction cosine is, how we might use it, and so on. There's a nice example in there doing projections in 3 dimensions, so the idea that we've met previously. It's exactly the same formula as you can see here, but that's just a nice little example that talks through that. And also we've got perpendicular distance and a nice worked example that just explains that there. And of course that's using projections. We did an example similar to that back in chapter 8 where we were using a projection of one vector onto the other to then find the perpendicular distance of that point to the line. Some questions from this exercise that go through this. And we move on to vector proofs in geometry. So this really builds on the extension 1 work in this, and I would say that assuming you're teaching both classes, now would be a good time in your extension 1 work to go and revisit that chapter review if you're not going straight off the back of it into this topic. So if there's been a bit of a gap, go back and look at the chapter review for chapter 8, particularly those questions towards the end. I said questions 15 and 16, which then lead nicely into this. There's only one example given in the textbook, so do go through it carefully with the class, but arguably that's all that's needed because they really need to just spend some time working on them themselves. The other thing that would set you up well for this chapter would be a quick recap of circle theorems and other stage 5 geometry. So the example that's there uses a bit of stage 5 geometry circle theorems, as you can see, and I think it is definitely worth recapping that. Remember, it is all now assumed knowledge. And this example is a nice example that then involves this idea of the dot product being 0, and also the fact that remembering that if you've got the modulus of something squared, then that's the same as it dotted with itself, and expanding these brackets using the dot product, all of which we've met in extension 1. So I suppose this is one particular area where harder 3-unit examples could sort of make its way in here somehow. We've got some examples there to try, and as I say, I think it's probably a good idea for them to spend a bit of time just working on these themselves, working on those proofs and practicing that way of thinking. And then we move on to the vector equation of a line. Now this is quite a large topic actually within this chapter. So this goes back to 2 dimensions as well as 3 dimensions. We need to link the idea of there being a point and direction, which is how a vector equation of a line works, with y equals mx plus c, and also parametrics come in here. So let's just have a look at the idea of how the vector equation of a line works. Suppose I've got r as any point on the line, then the displacement vector AR is going to be a multiple of P, where P is just that line there. So if I want to express the position vector of R, i.e. this particular point, which is a variable point on this line, then to get from O to R, I'm always going to go from O to A, and A is a point. I know this point on the line. I know the direction of the line, so I can do OA plus AR. Now AR can be expressed as lambda P, some multiple of P, and then I am basically saying that to get my general vector R of this line, I'm going to do A plus some multiple of P, lambda P, where lambda is a scalar. And that's the vector equation of a line in a nutshell. We've got going to a point on the line and then adding a generalistic expression for any point on that line. So here's an example. We've got a vector equation for a line through to -1. So we know it's going through that point, and we know the line's got gradient 3/4, and we're trying to find its Cartesian equation once we've got the vector equation for the line. So first of all, let's do it as normal without vectors. So just reminding ourselves what we do. We know that m is 3/4. We use the point gradient formula, and we get that it's 3x plus 4y is 10. So if we have a gradient of 3/4, that means we have a direction vector of 4, 3. Now that's a really important point to make sure they've got, that they understand that we can write a direction vector if I know the gradient, simply by doing what I've done there with a tiny little diagram. So if I've got a direction vector, then I can immediately just write down the vector equation. So R is the vector equation, and that's the usual letter used. So R is 2, 1, so that gets me to a point on the line, and then some multiple of that direction vector. That means that that will take me to any point on the line simply by varying lambda accordingly. So if I take a particular point, so take R is this particular point x, y, because this is me trying to find the Cartesian equation now, and I've also got that R is, and I could write this just by putting it in one bracket, 2 plus 4 lambda, or -1 plus 3 lambda, then I could equate those things to each other. I've got x is 2 plus 4 lambda, and y is -1 plus 3 lambda, and that's just parametric equations. So once I have an expression in parametric equations, then of course I can get the Cartesian equation by eliminating the parameter. And I find the same thing as I got before, which was just my nice check at the start. Other things we could be asked: find a point common to 2 lines. So here are my 2 lines. What points on both of them? Well, let's write both those lines this way, and then I can equate the different components. So it could be found by solving these 2 things, and basically that's just simultaneous equations, isn't it? So I can solve those simultaneous equations to find a value for s or t, doesn't really matter which, and whenever I've got it. So if I find t, then I'm going to put t back into this equation here, because that's the one with t in it, and I find that point, and I could always check that, just check that it fits into the other one as well. Let's go back to the NESA sample exam, because there's actually a nice example there in the multiple choice section that goes through which pair of line segments intersects at exactly 1 point. So now I've got this equation of a line, and notice they're all written in this form, that you've got your point and then you've got your direction vector and some multiple. So which pair of line segments has just got 1 point where they intersect? So let's go through this. The first thing I'm going to do is I'm actually going to change something, because it's slightly confusing if I'm going to try and equate this to have lambda in both of them. So I'm going to change one of the lambdas in all of them to a different letter to avoid that confusion and call it t. Once I've done that, then, if I take, let's A as an example to start with, I'm going to put u written this way and v written this way, and I'm going to equate those as simultaneous equations and see what happens when I try and solve them. And when I try and solve them, I get lambda is -3/4. Now, if lambda is -3/4, there's a bit of a problem because it's actually told me that lambda needs to be between 0 and 1, which means that it's not solvable, which means that they don't cross. And notice that these are line segments. They are not whole lines, hence the restriction on the lambda. Then we go on to B, so we say that no, that one's no good. Let's look at B. So same process again, I'm going to equate those two things, I'm going to solve them, and I find that there are actually multiple solutions when I try and solve those two simultaneous equations. So what does that mean? Well, it means that they must be the same line segment, or at least some of it must be the same. So that's a no as well, because it wants it to intersect at exactly one point. Next one, same process, try and solve them. And I've got t is a half, and when t is a half, lambda is a quarter. Well, that works, so that's fine. So that one is a yes. Now I could stop at this point, but I'm just going to check the last one to make sure that I haven't made a mistake somewhere. So let's do the same with the last one. And I find that there are multiple solutions again, and so that one is no good. So my answer is C. And then I might try quite a few questions, I would say, from this exercise. You want a bit of practice on this bit because we haven't met anything like this up to this point, so spend a bit of time on this one. And do a big range of questions. I've given you some suggestions here. So finally, we're on to 5G, equations of circles and spheres, and indeed looking at intersections of those things as well. So let's just look at what we mean by a sphere. So a unit sphere has got centre of the origin and it's got radius 1. That's what we mean by a unit sphere, in the same way you have a unit circle. So if I've got a particular general point on that unit sphere, then I know that the distance from O to that point is 1. In other words, I know that x squared plus y squared plus z squared is 1. So any point which satisfies that lies on the unit sphere. Now, if I've got it with a particular centre that isn't the origin, suppose it's HKL and the radius is something else, then I could write it like this. And that, I hope you can see that there's a clear link there with the equation of the circle. It's just extended into 3 dimensions. Now, the vector equation of a sphere is the set of points that are the same distance from a given point C. So I'm saying that my general point, take away the vector from O to C, is always going to be a certain distance. So it's always going to be this distance A. Now, if you have done the complex numbers drawing things in Argand diagrams, you will be able to make a nice link here in terms of how we draw, not in 3 dimensions, obviously in 2 dimensions, and how we draw particular regions in the plane around that. And there's a nice link there. Let's look at an example. Suppose we want to write down the equation of a sphere with a particular centre and a particular radius. We're going to do it in Cartesian form first of all, and then in vector form. So here it is in Cartesian form. You see we've just taken the points here. So this is the x coordinate, the y coordinate, the z coordinate, and the radius, and we've squared it there. In vector form, then we would take my r being my general point, and the distance between that and this other point is always going to be 6. That's what this is basically saying, isn't it? It's the distance between my general point on the sphere and the centre of the sphere is 6. And that's pretty much the definition of what a sphere is. So hopefully that makes sense. We might be asked to do something like find the intersection of a line and a sphere. So let's look at doing one of those. Well, this means we could write down some parametric equations. Remember that what we could do here, if we multiplied out this bracket here, I've got that the x coordinate is 2t, the y coordinate is t, and the z coordinate is -2t. Which means that if I want to find the distance, I just square them all and add them up, and I should be getting, as it says here, 9 being the particular radius squared. Now if I solve that, I get t is plus or minus 1, and so that means that the points are when t is plus 1 and when t is minus 1, and it makes sense that a line will hit the sphere twice. If you imagine throwing a javelin or something through a sphere, it should hit it twice, once on the way in and once on the way out. We might find intersections between a line and a sphere. This line is a little bit more complicated, and the sphere is also a little bit more complicated in that it's got a centre that isn't the origin, it's a different point. Same principle though, we're going to write down the parametric equations of the original line, and then we're going to apply those to the sphere, so putting them into that equation that we've got, and we solve them and we get t is plus or minus 3 root 2, and that means we can write down those points. So we have some questions to try from exercise 5G, and we might come back and do the chapter review when it's time for revision. Now if that's been a bit rushed, apologies. We've tried our best to get all of that together. Originally I think it was supposed to take an hour, it's been far longer than that. So I do hope this is useful to you. If you want any more details, PD for Maths is where we actually have a Vectors Online workshop that you can sign up for, and talks through all these things in much more detail, so do please go there and have a look. And I hope you found it useful.